I now call to order the Society's 2510th meeting in what is now the 153rd year since its founding on March 13th, 1871. Good evening, everyone. My name is Larry Milstein. I am the president of PSW, one of the oldest scientific societies of Washington, D.C., committed to providing a forum to further scientific understanding and inquiry. Welcome to our members, guests, and friends to tonight's PSW meeting and the lecture by Robert Smith. And before we begin, let's please thank our sponsors. The Society is grateful to PSW Full Year Series sponsors, PSW member Mike Helton and Helton Associates. Thank you, Mike. To series sponsor, PSW member Joe Schulman, hopefully spelled correctly. And to BAE Systems. Thank you, BAE Systems. We don't have a rep, but thank you. The Society needs your support to meet its expenses for the year. And if you have not given or feel you can give more than you have, please don't hesitate. You can do so through the website, and you can talk to any of the PSW officers who are in the room, and they will be happy to guide you to additional or support for us. I'm pleased to announce the following new members. Jawad Abdi, a senior portfolio management with Stand Together, interested in a wide variety of sciences, particularly psychology, neuroscience, and AI, who learned of PSW from doing research on the Cosmos Club on the web. So he said. Michael Rushford, a physicist and optical engineer with the Lawrence Livermore National Laboratory, interested in laser physics, lasers, laser optics, and applications of lasers to fusion energy production and defense applications, who learned of PSW from watching the video of the PSW lecture on directed energy technologies. And tonight's speaker, Robert Smith, who actually is a speaker member by virtue of his participation in PSW's celebration and panel of speakers on Hubble's 25th anniversary, but we're happy to have him be doubly a speaker member. Welcome them all to membership. All members are entitled to a signed copy of Volume 17, first edition of the Bulletin of the PSW. If you've not received yours, please come see me after the meeting. If you're interested in membership, you can access a membership application on the PSW website by clicking on the Join button on the home page at the upper right-hand corner. It's hard to miss. And if you're here in the Powell Auditorium, you can access the application using the QR code on the business cards on the tables at the back of the room. If you have any questions, please ask me or any other member of the General Committee here tonight, or email us, correspondingsec@psw.org, Recording Secretary Scott Matthews cannot be with us tonight, but he did prepare the minutes of the 2509th meeting and the lecture by Mike Seablum and Mike Folkowski on remote sensing of wildfires. Our Vice President, Robert Thompson, is kind enough to read those minutes for us. Robert, the stage is yours.
On February 7th, 2025, members of the Society and guests joined the speakers for a reception and dinner at 5:45 p.m. in the members' dining room at the Cosmos Club. Thereafter, they joined the other attendees in the Powell Auditorium for the lecture proceedings. In the Powell Auditorium of the Cosmos Club in Washington, D.C., President Larry Milstein called the lecture portion of the 2509th meeting of the Society to order at 8:05 p.m. Eastern Time. He began by welcoming attendees, thanking sponsors for their support, and announcing new members. Scott Matthews then read the minutes of the previous meeting, which included the lecture by Scott Wolk titled Highlights of the X-Ray Universe, Chandra's 25 years of observation and more to come. The minutes were approved as read. President Milstein then introduced the speakers for the evening, Michael Falkowski of NASA's Wildland Fires Program and Michael Seablum of NASA's Science Mission Directorate. Their lecture was titled Remote Sensing of Wildfires. The first speaker was Michael Seablum. He began by saying that the long-term monitoring of the Earth is of critical importance. As an example, he showed a video depicting the annual minimum Arctic sea ice as measured from space from 1975 to the present. He claimed that the Arctic sea ice in the summer could be completely gone by 2040. He described the 4 elements of NASA's Earth Science Division: flight, research and analysis, Earth action, and technology. Seablum showed a graphic of the Earth fleet, all of NASA's Earth-observing satellites, past, present, and planned. This included 33 separate missions, some with multiple spacecraft, 7 ISS instrument packages, 6 CubeSat projects, and 4 JPSS instruments. Seablum then gave details about several specific missions. He began with the PACE mission, showing images of phytoplankton and aerosols in the Aegean Sea and the Black Sea. He showed hyperspectral images of Florida before and after Hurricane Helene, demonstrating the upwelling of sediment and plankton resulting from the storm. Seablum showed data from SWOT, surface water ocean topology. He indicated that these data will enhance our understanding of small-scale ocean circulation, hydrological cycles, and freshwater management. Seablum then discussed the process by which these programs evolve from concept to a final mission. As an example, he gave details of the PACE mission, beginning in 2008 with the ORCA instrument, through the development of a compact hyperspectral imaging telescope, to the hyperangular rainbow polarimeter, HARP-2, to the set of instruments ultimately deployed on PACE. Seablum gave similar details about the development of the technology for the SWOT mission, including the Advanced Altimeter for Ocean Science in 1998, the development of a Ka-band radar interferometer in 2007, the multi-frequency antenna and receiver downconverter, and finally AirSWAT, a synthetic aperture Ka-band radar interferometer flown in a Beechcraft King Air. Seablum then discussed future research areas for ESTO, NASA's Earth Science Technology Office. These included lasers, passive microwaves, passive optics, radars, quantum sensing, and metamaterials. He described the use of quantum gravity gradiometers to measure terrestrial groundwater storage, ice sheet mass change, glacial isostatic adjustment, and groundwater flux. Seablum ended his portion of the lecture by discussing the roles of modeling, artificial intelligence, and machine learning in earth science. The remainder of the lecture was presented by Michael Falkowski. He began by saying that he had spent several years trying to figure out how best to use Earth observation data to support a wide variety of resource management issues, including fighting wildland fires. He showed an animation of NASA's Earth observation fleet, indicating that there are approximately 25 or 30 missions with spacecraft currently in orbit. Falkowski said that wildland fire management not only involves monitoring active fires, but also includes monitoring factors in the pre-fire and post-fire environments. He showed several animations of data acquired by NASA satellites, including 1 year in the global fire life cycle, carbon monoxide levels from the Canadian wildfires in 2023, and the progression of a wildland fire in California in 2021. He showed several graphics which indicated increases in the number of wildfires, the land area affected by these fires, and the intensity of the fires over the past several decades. Falkowski then discussed the increase in extreme fire events. He indicated that dry conditions and high winds created what he called fast fires, which have been responsible for as much as 78% of the structures lost to fire in a given year. He discussed the Paradise fires in California in 2018, saying that post-fire analysis indicated that most of the vegetation did not burn and that the houses themselves were the primary fuel. He showed examples of houses which survived these fires, saying that the homeowners took several preventative actions to decrease fire risk, including installing metal roofs, moving vegetation away from the house, and using non-combustible materials such as gravel and concrete. Falkowski then discussed proactive wildland fire management. Specifically, he mentioned building resilient communities, forest thinning, prescribed burns, and restoring ecosystems. He claimed that while some wildland ecosystems suffered long-term damage from fires, some have evolved to withstand occasional fires and even benefit from them. And finally, Falkowski discussed the overall mission of NASA's Wildland Fires program. investing in foundational technologies, studying Earth systems, conducting applied research, and transitioning mature technologies to fire management agencies. As a specific example, Falkowski discussed the development and deployment of the FireSense program, which includes airborne radar, thermal imaging, spectroscopic imaging, unmanned aerial systems, and prescribed burns coordinated between NASA, NOAA, and USFS, the United States Forest Service. The lecture was followed by a question and answer session. A guest asked if there would be more high wind fires or fire tornadoes in the future. Falkowski responded, yes, we expect to see what we saw in LA recently again and potentially more frequently. A guest on the live stream asked if it was time to stop building houses out of materials like wood, shingles, plastic, and foam. Falkowski responded that materials play a big role in reducing fire risk, but that metal roofs, moving vegetation away from homes, and something as simple as placing a screen over the eaves can make a big difference. A member asked whether more frequent overflights would provide more fire predictive data. Falkowski responded that more frequent observations would be, quote, game-changing for fire modeling. After the question and answer period, President Milstein thanked the speakers and presented them with PSW rosettes, signed copies of the announcement of the talk, and signed copies of Volume 17 of the PSW Bulletin. He then announced speakers of upcoming lectures, made a number of housekeeping announcements, and invited guests to join the Society. He adjourned the 2,509th meeting of the Society at 10:02 p.m. Eastern Time. The temperature in Washington, D.C., 5 degrees Celsius. The weather was fair. Audience in the Powell Auditorium, 54. Viewers on the live stream, 23, for a total of 77 concurrent viewers. Views of the video in the first 2 weeks, 207. Respectfully submitted, Scott Matthews, Recording Secretary.
Thank you, Robert, and thank you, Scott, if you're listening. Are there any comments or corrections to the minutes as read? I think Michael Falkowski is in the audience somewhere, and if he has any corrections, this would be a good time to let us know. Hearing none, I will assume this is a very accurate and succinct summary, as Scott usually prepares for us, and I will accept a motion to accept it as read. Second, all members in favor? All members opposed? Minutes are accepted as read and will be posted to the website in due course. And we now turn to tonight's lecture by Robert Smith. Robert is a professor of history at the University of Alberta, Edmonton. For many years before that, he was a staff member of the U.S. National Air and Space Museum. Actually, I should say U.S. Smithsonian Air and Space Museum. In addition, he has served as an advisor to OECD, NASA, and the National Academy of Sciences. He is an author of over 50 research papers, most of them solo, and author of 5 books, and co-editor of 3, some translated into French, Spanish, Italian, and/or Chinese. Throughout his career, Robert has been a student of early 20th century astronomy and cosmology. And his first book was The Expanding Universe, Astronomy's Great Debate, 1900 to 1931. But his chief interest has been the history of space astronomy and its emergence as a megascience. His studies of the pre-launch history of the Hubble Space Telescope are summarized in his book, The Space Telescope, a study of NASA, science, technology, and politics. He has been following the James Webb Space Telescope project since its conception, and he's working on a history of the telescope. We'll be hearing tonight some of his findings and conclusions now that JWST is at home in space and conveying data to astronomers all over the world. Among other honors and awards, Robert was a fellow at the National Humanities Center, held the Smithsonian's Lindbergh Chair of Aerospace History, and was a AAAS Sarton Lecturer. He was awarded the AAS Doggett Prize, the History of Science Society's Watson Davis Prize, and the Bung Prize, I think it's Bunge, Prize of the Society of German Chemists and the German Society for Physical Chemistry. He earned a Bachelor of Science degree at Queen Mary College, University of London. Part 3 of the mathematics tripos at the University of Cambridge. Now, for those of you who don't know, that is one of the most difficult courses of mathematical studies in the world, and it's quite something to have earned that. And a PhD in the history and philosophy of science at Cambridge University. And with that, I'll note that all questions will be fielded after the lecture during a Q&A session, and the stage is yours, Robert.
Well, thank you for that very generous introduction. Begin with a sad story. What a pity it was that the James Webb Space Telescope was cancelled in 2011. It was going to revolutionize astronomy, particularly in the areas of the study of exoplanets, the study of early galaxies, brought down by budget problems, sniping from other scientists. It met an unfortunate end, very like the end that was met by the Superconducting Supercollider, for those of you who can remember the early 1990s. So what's the effect on astronomy? It's left the Hubble alone. Many of the problems raised by Hubble can no longer be addressed by Webb because Webb doesn't exist. The community of users that would have taken on Webb, where do they go now? And it underlines what a fragile business space astronomy is when you have a project that might consume 20, 30 years of somebody's career chopped off early. What then happens to that particular community? Again, with the community involved with the Superconducting Supercollider, that community has never really recovered decades later. Well, of course, I'm fibbing. I'm sorry. It did not end. But I think one of the things I want to try and get over is that somehow it's assumed that these kinds of projects are inevitable. It's kind of organic that something like Webb will follow the Hubble Space Telescope, and the Hubble Space Telescope will follow other earlier kinds of space astronomy projects. So what I'd like to bring into this story is what we might call the element of contingency. We're not looking at inevitabilities. Things could have turned out differently. And to look at Webb's history, what I would like to do is go back some before I take a longer run forward and look at the development of Webb and carry things through to launch in some of the first observations with Webb. I have to show my face to my colleagues, my history colleagues on Monday morning. So let's go back to the 19th century. They think I'm a lunatic for doing this stuff, but the key questions for us: why are some really big instruments built and others left on the drawing board? What is it that moves them forward? How do you do this movement from the drawing board to an operating tool, an operating instrument in space? Now, when I say here, I'm largely looking outward rather than inward, so we're not going to get a lot on what you might call the kind of internal engineering of Webb. That's absolutely fascinating as well, but in an hour, I've got to make some choices here. And what I've decided to do to make this history manageable is not try and cover everything, doing a little bit on each year, what was the most important stuff in this year, and then kind of moving on. I will try and present things in terms of what I call key moments. And our first one, as I say, I can hold my head up with my colleagues and say, I did something about 1833. So why are we going back to 1833? I just want to emphasize what a remarkably successful business astronomy has been in the last 2 centuries. This is somebody, a professor of mathematical sciences in Britain, John Narian, and he's looking at the future of astronomy. What is astronomy about? I mean, where is the future? What will happen? Human ingenuity, he thinks, will probably in future be able to accomplish little more than an improvement or in the means of making observations or in the analysis by which the rules of computation are investigated. It's over, right? It's over, almost. We fiddle a bit, we dot the I's, cross the T's, but the big story is over. And the big story is being provided by Isaac Newton with the universal gravitation. You work out the implications of that. Fine. And this is before the first parallax of a star, the first distance to a star beside the sun, was actually measured. But this is the conception of astronomy that's in play in 1833. And just to show that that was not a kind of one-off, this is Agnes Clerk, who's the leading historian of astronomy really in the 19th century, looking back from 1885 at the earlier time of astronomy. There were those who began to regard it as a science which from its perfection had ceased to be interesting, whose tale of discoveries was told and whose further advance must be in the line of minute technical improvements, not of novel and stirring discoveries. Right. What a transformation. All right, I've leapt forward a bit, but I can still make my colleagues happy because I'm only making it to 1905. What happens in 1905? This is a lecture by George Darwin, who was the son of Charles Darwin, very distinguished astronomer, geophysicist. And what's he arguing? Was it not as futile to imagine that humans can discover, as he puts it, can discover the origin and tendency of the universe as to expect a housefly to instruct us as to the theory of the planets? Questions about the origin of the universe, that's metaphysics, and we don't do metaphysics. Right? I mean, it would be pointless. So again, the conception of astronomy, the ambitions of astronomers at this period early in the 20th century are so limited, but these particular issues that Darwin is talking about would actually be addressed very soon. And there will be the conception, for example, of the expanding universe that develops in the late 1920s, early 1930s. But again, now we have tools like Webb, which can see remarkably close to what astronomers will describe as the Big Bang, very early period in the history of the universe. These kinds of questions were simply inconceivable at an earlier period. There was also, at the time that Darwin was lecturing, there was a single galaxy universe. That was the model. There is one visible galaxy in space. There may be there may be other galaxies, but they're not visible. Nobody has seen a galaxy beyond our own Milky Way galaxy. So this is our own galaxy. It's surrounded by nebulae, and that's a visible universe. That's it. Right? That's it. What an utterly different conception astronomers hold today. And how did this come about? To a degree, it's a story of large, powerful telescopes, more powerful than anything that had been built before. Many of you, I'm sure, will recognize this is the Mount Wilson 100-inch telescope with which a range of fundamental discoveries was made early in the 20th century. Patronage was being provided by the Carnegie Institution of Washington, and there we have Andrew Carnegie dispensing money for all sorts of things, but he also provided initially $4 million of steel stock to found the Carnegie Institution of Washington, which was a massive boost for the development of science in the United States. And it was transformative, in fact. And with that, the reason I showed this is almost 100 years ago. I mean, 100 years ago, it was possible to argue that there is only one visible galaxy in space. But as many of you, I'm sure, will know, there was discovery by Edwin Hubble in late 1923, confirmed early 1924. So this involved the Andromeda Nebula. Here we can see planets forming. I mean, it's obvious, right? They're planets. I mean, that's what people believe. This was shown at the Royal Astronomical Society in 1888. And there were cries, it said, in the report of the meeting, there were cries of the nebula hypothesis made visible. That is, what are we looking at? We're looking at a star being born out of a swirling cloud of dust and gas, and here we have planets forming. So this is Hubble's discovery plate, where he's got var for the variable star, the first Cepheid variable to be discovered in the Andromeda Nebula. And the point about the Cepheid variable is that if you use Henrietta Leavitt's period luminosity relationship for this variable star, you can work out the distance. It's as if this star is standing there waving a flag saying, hello, you can easily work out my distance here. And the demonstration was this was a galaxy of stars far beyond our own galaxy. The universe, in fact, by the late 1920s, it was generally accepted the universe is full of galaxies, but it was not so even 100 years ago. So let's leap ahead. My colleagues are still okay. It's getting a bit dodgy, 1946. Let's go to New Mexico. Launch of one of the captured V2 rockets that have made it back to the United States from Nazi Germany, and some of the earliest experiments in rocketry also carried along scientific instruments. And there were even some astronomers who began to investigate how can we use vehicles that get above the Earth's atmosphere to study the cosmos. How can we escape from this position below this ocean of air, which messes up so much of our observational ranges? The problem with the V2 as a device to do astronomy is it goes up and it comes down and it makes a big hole. And the early pioneers in space astronomy decided, well, maybe we'll let things develop a bit further before we go back to this. But certainly in the late 1950s, early 60s, we have a range of devices which are employed to carry scientific instruments, astronomical instruments above the Earth's atmosphere, and or very high in the Earth's atmosphere. So we have balloons. Here's an X-15. Some of the X-15 rocket planes carried ultraviolet spectrographs behind the pilot. So when the X-15 got very high into the atmosphere and practically out of the atmosphere, there were observations of, for example, the sun in the ultraviolet. And some of you may be able to guess what this is because we have a rocket and a balloon. So what have we got? A raccoon, exactly. The NRL veterans show themselves. Right, very good. And so it's kind of opportunistic. It is, okay, let's develop these instruments. They're sensitive in these particular ranges. What can we see? Moment 4, you can guess what this is as soon as I put the date up. So let me not linger too long. But it's Sputnik 1. Launch of Sputnik 1 in orbit around the Earth, which produces, of course, a response. Early space activities were very much predicated on the Cold War and competition, Cold War competition. But there was an awful lot of science that was done as well. I mean, that's not the main reason for so many of the NASA programs in the late 1950s, early 60s, but science goes along for the ride in many respects. New patrons enter, or patrons enter on a level that's never been seen before. I mean, the federal government now is pouring a great deal of money into science from above the Earth's atmosphere. And this is a chart that was used by lots of NASA managers over the years to demonstrate the importance of getting above the Earth's atmosphere. What kinds of ranges of observations can you make? If you're going to do X-ray astronomy, you've got to get above the Earth's atmosphere. If you're going to do most of the infrared range, you've got to get above the Earth's atmosphere. Gamma ray astronomy and so on, you've got to get above the Earth's atmosphere. So the 1960s is really a kind of period of pioneering where people were building their instruments, getting launches, ideally in satellites, but if not in rockets, and making their kind of initial forays into these new wavelength ranges. We have the emergence of what I've called here panchromatic space astronomy. That's the infrared astronomy satellite on the left, 1983. Uhuru, which was an X-ray satellite, the first X-ray satellite for astronomy, 1970. But there are already plans developing for what would become called the Hubble Space Telescope. And quite early, those plans were connected to the space shuttle. The point being that, and this is obviously a very early concept for the space shuttle, the point being that if you're going to build something like the shuttle, where are the payloads? What's the point? There are going to be so many launches, it was argued. We need to have worthwhile payloads that will go along with the shuttle. So this was something of great concern, for example, to the Office of Management and Budget. It becomes a kind of what you might call selling point for the advocates of putting a large optical ultraviolet telescope in space. This is what was called the Large Space Telescope in the late 60s, early 70s. It was going to have a mirror 3 meters across. It was going to be serviced by the shuttle. It would be taken into orbit by the shuttle, then it will be brought down for periodic work, returned to orbit, and so it would be kept at the state of the art as a result of that. And at the end of its career, I know because I was in the meeting where we discussed this, it will be collected and brought down and put in the Air and Space Museum. That plan, sadly, proved a bit too expensive as the shuttle costs began to rise. And if we leap ahead to the actual construction of the Hubble Space Telescope. This is the famous Hubble mirror. And those of you with acute eyes may have seen the backup Hubble mirror in the presentation that we had, or the rolling presentation. And so there was the Ellen Stofan image, which had the backup mirror for Hubble. She's standing in front of it, which is, I don't know if it's still there. I wasn't able to get to the museum today. But the backup mirror for the Hubble Space Telescope is on display in the National Air and Space Museum. So this is the actual mirror. It would have been better if they'd been reversed, because this one contains the famous flaw, the spherical aberration. The mirror is just a little bit too flat at the edges. I mean, it's perfectly shaped, but perfectly wrong. And it leads to, after the launch in I included this just to give us a date here, 1989, Hubble had not been launched because there'd been, of course, a shuttle disaster in 1986. And it was probably a good thing Hubble did not launch in 1986. There were still a number of issues that had got to be worked out. But Hubble finally launched in 1990. And this is a 2.4 meter optical ultraviolet with a little bit of infrared in terms of wavelength ranges. And so even before Hubble is launched, there is my fifth moment. September 1989. There's a conference at the Space Telescope Science Institute, which is just down the road in Baltimore. And a small group had been at work at the Institute planning a successor to the Hubble Space Telescope. The reason for this planning that was going on was because the then director of the Space Telescope Science Institute was somebody called Riccardo Giacconi. He was initially a cosmic ray physicist before he switched to X-ray astronomy. He was fully aware that big space missions take a lot of time to complete. He wanted work to begin on planning a successor to Hubble even before Hubble was launched. And so this group began meeting in the mid-1980s. As I say, it's just a handful of people at the Space Telescope Science Institute. One of their products, for example, is this paper by somebody called Pierre Belli, a 10-meter optical telescope in space, a much bigger telescope than Hubble. This is in the realm of feasibility study, really. It's what might be possible. People are thinking out some possible ways you could follow Hubble. There's some of the products of the conference, not the people on the right. I'll talk about them in a moment. But we have a 10-meter space telescope, and we've got a telescope on the moon. And I've got a large collection of papers to do with telescopes on the moon, none of which have seen the light of day. But it's a regular sort of telescope that's studied. But at this point, this new telescope was called, or what was hoped would be the new telescope, was the Next Generation Space Telescope. That is something that will go beyond the Hubble Space Telescope. And why do we have stuff on the moon? It's because 1989, this was a signing at the National Air and Space Museum, where we have President Bush signing a new space policy, and we have the Apollo 11 astronauts, along with the then NASA administrator Richard Truly here. And the idea is to go back to the moon. People will be going back to the moon, hence the astronomers take their cue from that and begin to consider large telescopes on the moon. And this one was something of about 16 meters for the main mirror. So this conference brings together quite a lot of people. It's about 100 people who were considering what can we do for the successor to Hubble. It's still about a year shy of the actual Hubble launch, which is moment 6. Hubble launched, and Canadian content in the form of the shuttle arm. But we have the launch. Here's Hubble being deposited in space. Solar arrays to collect sunlight and help produce electric power for the observatory. And I suspect many of us know what's going to happen next. It's spherical aberration with all these tendrils and odd-looking things. And spherical aberration means that the mirror is flawed. And so instead of a nice, tightly focused beam of light here, we've ended up with these kind of rings and tendrils and odd-looking things. Something's gone badly wrong. And NASA takes a pasting. And this is actually a pasting that goes on for months. Star-Crossed, NASA's $1.5 billion blunder. A Herblock cartoon where Hubble is taking an eye test. Never mind, come back and give the examination to NASA. And there's a lot of introspection at this point. And there's a great deal of concern, more broad concern, to do with is the United States falling behind its industrial competitors, in particular Japan at this stage. Are the Japanese getting a leap on us? If NASA cannot build a Hubble Space Telescope successfully, how can it possibly build an international space station or some sort of space station? So this reflects very broadly on the potential future or futures that might be available to NASA. Maybe the low point comes with Naked Gun 2.5. How many people are prepared to admit they've seen this fine movie? Yes, don't be shy. It's all right. You know, you can claim you've watched it purely for historical purposes. It's okay. So in Naked Gun 2.5, we have people who visit the Blues Bar. And the Blues Bar is, not surprisingly, the place to go where you have the blues. And they have pictures of various disasters along the wall. There's a Hindenburg, there's a Titanic, there's Michael Dukakis. And at one point there is the Hubble Space Telescope because it had been pegged as a massive failure. But it's not, in the end, a massive failure. And because it's a kind of comeback story, I think it carries actually a lot more force, that here is a comeback where a telescope which had been dismissed, had been derided, had become an object of fun in Naked Gun 2.5 and a lot of other kinds of venues as well, turns out to be a remarkably successful scientific instrument. And it's made in large part by the maintenance missions that were run. The idea with the Hubble had always been, we will maintain the telescope, keep it close to the state of the art because astronauts will go up on a regular basis, change out instruments, failed components could be switched, And so we have a launch, 1993, where astronauts go to Hubble, capture it, put it into the payload bay of the space shuttle, change out instruments, also change the solar arrays and do a bunch of other things with the telescope. You get a call from the then president and the vice president, that's the crew, talking to President Clinton and Vice President Gore. And the result is a success. And we have the kind of transformation of Hubble. And a large part of this transformation is what you might call mediated by the kinds of images that are produced for public consumption. And so I would argue that these images have an enormously important role to play, not just in carrying the wonders and mystery of the cosmos to a very wide audience, helping to justify why have we spent all this money on this telescope, but demonstrating it actually works. And from a telescope that was derided, that was supposedly a failed instrument, it now becomes really a demonstration of American scientific and technological prowess. This is arguably the most famous of Hubble's images, the so-called pillars of creation. This is Jupiter, which has been hit by fragments of comet Shoemaker-Levy in 1994, which had been examined by the repaired Hubble Space Telescope. And so the images are making a political statement, as well as a statement, as I say, about the nature of the cosmos. And the telescope becomes, I think it's fair to say, becomes a celebrity. And now I'm afraid I failed because I forgot to put on the item of clothing that I normally do when I get to my undergraduate lecture on Hubble. And the students have to guess which item of clothing I'm wearing. So my Hubble Space Telescope, more precisely my Pillars of Creation socks, are sadly in the hotel room. I can't do my big moment where I roll up my socks and pants and demonstrate I'm actually indeed wearing one of these items. But it gets to the point the telescope becomes a kind of cultural symbol, but it's a cultural symbol of success, not of failure, as it was shortly before. So the telescope has been transformed. And the prospects, and what this means for us, is that the prospects of a successor to Hubble have been transformed. Success begets success is part of the message of tonight's lecture, in that if Hubble had not been fixed, if the astronauts, when they went to Hubble in 1993, had not been successful, if the Hubble had kept performing at its previous level, it's hard to imagine a successor to Hubble following, at least in any kind of reasonable time scale. But Hubble is a success. So now that opens possibilities for a successor. The Superconducting Supercollider, which gets cancelled in late 1993, is not followed by a successor to the Superconducting Supercollider. That's it, right? And I suspect the same fate. I mean, it's a what-if question, so who knows? But it's hard to imagine anything like a JWST turning up for many years after the Hubble failure. So let's go to moment 7, because that is the report. Many of you, I'm sure, are familiar with the idea of a decadal survey, where you have plans examined for particular areas in science. Astronomers have been doing this really since the mid-1960s, or at least versions began in the 1960s, where you do a decadal survey, you identify the best prospects in terms of what projects would most benefit the development of the science within certain limits of budget, time, and so on. And so we have the Bacall Committee meeting in the early 1990s. This is a committee to examine the future of astronomy. And this decadal survey argued that the 1990s will be the decade of the infrared. The coming region in the electromagnetic spectrum should be the infrared. There were huge improvements that the committee could see in terms of the detectors for infrared light. The detectors were getting much larger, basically. You could do a lot more in terms of infrared in the late 1980s, early 1990s than you could have done a decade earlier, because the technology has improved so much. And having reached this point, it's useful to just take a moment to step back, because we're facing this fundamental question. I mean, who decides which instruments to build, which ones to pick? How do people get their choices put into effect? How do you move from the drawing board, some bright ideas, into an actual working observatory, particularly when it is likely to take a long time, cost a great deal of money? What's the role of the relevant government agencies, industrial contractors? If you can't get the industrial contractors interested and engaged, then you aren't going to have much of a project, particularly if you're talking about a very big space astronomy project. What's the position of the astronomical community? Can they come together to make decisions and say, yes, this is our number one priority, this other telescope down here is still really interesting, but we're putting it at number two. You've got to work out all sorts of compromises as a result of this. But the state of infrared astronomy in 1991 was really attractive to a range of people. And as I say, there was this decade of the 1980s when the detectors, the light detectors for detecting infrared light, had improved enormously. Staggering advances, it says here, in scientific capability. Not just the detectors, but this is a very well-known astronomer, Malcolm Longair, making this call in 1991, which pretty much the Bacall Committee agreed with. All aspects of instrumentation, mechanical, electronic, optical, and cryogenic design, because infrared detectors need to be kept cold. But he's complaining here that this kind of awareness is not shared by that many people amongst the astronomical community. The state of play of infrared astronomy is such that it's, as he puts it, still the pioneers and aficionados who are using these wonderful new infrared instruments. He's urging his fellow infrared astronomers, and here he's wearing a hat as an infrared astronomer, go out, you've got to sell this project. If you can't get general cooperation and agreement, the project is not going to move forward. All right, that's his warning here. So where these infrared detectors in development come from? A lot of it comes from developments engaged with what you might call national security areas, and there's President Reagan giving the famous speech, the Star Wars speech. And if you're interested in ballistic missiles and detecting ballistic missiles when they take off and when they come back down, there are particular points on their trajectory when they will give off specific infrared signatures. And what we're seeing here is that in many respects, we can take space astronomy as a gift of the Cold War, because the detectors that infrared astronomers will employ are not simply those developed for national security purposes. They've got to be worked on, but there they are to be worked on, and you can do an awful lot with what you're being given, in effect. So SDI monies for, this is from a very interesting paper by a distinguished infrared astronomer, Martin Harwitt. And what Harwitt is arguing here, SDI monies for infrared-related studies between 85 and 92, maybe 7.5 billion. If you add up the monies going to infrared astronomy from all of the space agencies in the world, it's 3.7 billion. And that's all infrared astronomy combined. So there's this enormous boost for infrared astronomy from these national security developments. And just to underline these points, the ICBMs in their boost phase, the key signals are near 2.7 and 4.3 microns. Mid-course trajectory is 10 microns. And then when their heat shields are glowing, about 5 microns. And so where are the most effective infrared detectors to be found? No prizes for saying probably between 1 and 5 microns, right? Which is good for astronomers, because that is the region that lots of astronomers are extremely interested in, because distant galaxies, the light of distant galaxies is going to be redshifted, and so it's no good trying to detect them in ultraviolet light, really. How much better to have infrared detectors that are going to detect these redshifted galaxies which are incredibly distant from the Earth. So again, to underline, Hubble also benefits from this link to national security. This is an interview that was done with George Keyworth, who was President Reagan's science advisor. I don't know if anybody can recognize, whoops. Kremlin, yes, and you know, this image isn't doing justice. This is a KH4 image, Keyhole 4, for the reconnaissance satellite. This is a program that was declassified in 1995, and you know, you look at the image, you can see people lining up to see Lenin in Lenin's tomb in this particular image. But you know, what is Keyworth arguing here? There's no question that it would have been a very much more difficult task to build Hubble if we had not already acquired considerable expertise in both talent and industrial manufacturing. Hubble is new, but it draws upon technologies used for military systems, right? So that is an open public interview in 1985. So Hubble was definitely benefiting. You may want to make an argument that JWST got ahead of the curve and was doing a lot of development work for itself, rather than kind of following in the slipstream of these national security developments, which may be one of the reasons why Webb ran into some budgetary issues. But you're not going to answer that question with an accent like mine, I suspect. So, moment 8. January 1996. There'd been a committee established chaired by Alan Dressler from the Carnegie Observatories. Not surprisingly, it's called the Dressler Committee. And they meet. And the reason there's a Dressler Committee is that in the early 1990s, AURA, which is the organization that runs the Space Telescope Science Institute, as well as a number of other facilities, scientific facilities, was desperate to get something, anything, moving. And they put together a committee with the assistance of NASA, and it was designed to look at what are the possibilities for doing astronomy on the ground and in space. Where are the new exciting possibilities? And the committee starts meeting 1993. That's even before Hubble has been fixed. But they gain momentum once Hubble is fixed. And Dressler and his committee work on a report, and it plays to be not just good, but if you can be lucky as well, that's great, because what happens in 1995 is, for astronomy, the first definite detection of an exoplanet. Right? 1996, we have the Martian meteorite and the possibility of life, or at least ancient life, on Mars. And so Dressler and his committee put together this report, and it focused on origins. And NASA actually establishes a group in NASA headquarters and a program, the Origins program, which is really a very successful program, with the Next Generation Space Telescope as one element. So the Next Generation Space Telescope is moving again, having been brought back to life, in effect, by this successful repair mission to Hubble, and then the follow-up with this particular report. And it's, even now, I think it's well worth reading. It's really quite a poetic report. It's not the thing that you would normally see in a kind of scientific report saying these should be our priorities. But origins should be the guide. But at the same time, they're really concerned they've got to break the cost curve for Hubble. If they can't break the cost curve, that is make it a lot less expensive than Hubble per pound, this mission is not going to proceed, because what's happened in 1991, we've got the end of the Cold War, so science funding has been struggling. That is in part represented by the cancellation of the Superconducting Supercollider in 93. The Dressler Committee argue for a new telescope with a main mirror, primary mirror, at least 4 meters. It should be focused on the infrared. There's also general agreement that there needs to be a new way of doing infrared astronomy. You've got to keep your telescope and your detectors cold if you're going to do infrared astronomy. So one way to do infrared astronomy is you put it in a large dewar, in effect, keep things cold. But that is enormously expensive. So there was a mission which ends up being called Spitzer, the Spitzer Space Telescope, I think. And it goes through various stages. And it is simply too expensive when the design is focused on putting the telescope into a giant dewar. They end up switching their approach. This is something that has been argued by a range of other people, but it is called passive cooling. You send your observatory up and let it cool down, rather than active cooling, sticking it inside the dewar. And this is transformative for space astronomy. So you've got now these new detectors which are much more efficient, much larger area. You've got this new approach which is much less expensive, the passive cooling. And so it seems things are starting to come together here. And this new, or the potential of a new telescope, catches the eye of the NASA administrator, Dan Goldin, gives a speech to the American Astronomical Society. Our next big step in space astronomy is the infrared. And in this speech, he sees Alan Dressler, who's led the committee, arguing for this successor telescope. All he wants is a 4-meter. And I said to him, why do you ask for such a modest thing? This is not normally what NASA administrators say to people, as far as I've been told. Why not go for 6 or 7? We have years to work this out. Right? And there is a very positive response. This isn't addressed to astronomers. This is to the American Astronomical Society. And not surprisingly, he gets a standing ovation. Well, what would you say? Build this thing 6 or 7 meters. Don't mess about with something small. Go big. And these are some of the early design notes by Pierre Belly, who I referred to a little bit earlier. He was working away in the 1980s, even mid-1980s, on possible designs of what was still being called the Next Generation Space Telescope. And now you've got a dedicated group that is established because the NASA administrator really likes this project, and things are starting to move in NASA headquarters, as well as at the Goddard Space Flight Center, as well as at the Space Telescope Science Institute in Baltimore. But there's always a concern about cost, because how do you break the cost curve, as it's called? How do you break the Hubble paradigm? Because it seems you're going to have too expensive an instrument. And the cost of getting Hubble to the launch pad and away, if you don't count the spacecraft anyway, is something in current year dollars, it's about $4 billion. We can't spend that kind of money, Goldin argues. We've got to do things less expensively. So the people working on this project are consciously trying to do things differently to the way that Hubble was done. And I can come back to that later if anybody wants to go further into it. But let me just point out that we have here strategies for cost containment, breaking the Hubble paradigm, comparison of HST and NGST, comparison of Hubble Space Telescope and the Next Generation Space Telescope. And so it's almost as if they're trying to create almost an anti-Hubble. Hubble is great. I mean, it's done remarkable things. It's shown us what we can do, but we can't do things in the same fashion with the successor. Okay, moment 8. 2 Mars spacecraft lost. Goldin, when he became NASA administrator, introduced a new engineering philosophy, faster, better, cheaper. Many of you, I'm sure, have come across this. Some of you have lived it. And in 1999, there were 2 Mars spacecraft that ended their missions prematurely. And that was pretty much the end of faster, better, cheaper. I mean, before then, between 96 and 99, there was something like 16 faster, better, cheaper missions. 6 failed, which is a kind of unacceptable number. Even if you could justify it technically, okay, we fly one, it doesn't work, we build another one, it is politically enormously damaging. So the philosophy for the Next Generation Space Telescope now becomes more conservative, I think. You cannot be taking these kinds of risks. Moment 10, some of you are in this picture, which is the start of what is now called the James Webb Space Telescope project. These are people meeting at the Space Telescope Science Institute. The project is underway. There is a prime contractor selected. It's TRW, but that very quickly becomes absorbed into Northrop Grumman. The Goddard Space Flight Center is going to be involved. The Space Telescope Science Institute is going to be closely involved as well. And there's a lot that, of course, I could say about what goes on between 2002 and the actual launch. But let's go to July 6th, 2011. Because at that point, JWST zeroed out of the budget. The project, unless things are changed, is over. So this gets to my kind of ham-fisted attempt to be introducing the element of contingency at the very start of the lecture. Because here we have a really key moment, I think. If this decision is not overturned, the mission is done, more or less. And why does Frank Wolf's committee decide that they're going to zero out JWST? It's billions over budget, plagued by poor management, he says. But on the other side in the Senate is Senator Barbara Mikulski. She's not a senator in this picture, but she is here, and she's a key figure because she really is a strong advocate for space astronomy. And if there's one person you could describe as a single point failure for the James Webb Space Telescope project, it would be probably Senator Mikulski, I think. Say she had decided to retire in 2005 or something and left things behind, who knows quite what would have happened to the project. But she fights to get the telescope back into the budget. It proceeds, but it's being given a very firm budget number that it has to stick to. But a key point here is if you are going to turn around these kinds of political decisions, at least in the 2010s, you've got to establish a coalition of supporters. You cannot just have a small group. You've got to, if you're talking about astronomers, have an entire community involved. And just as with the Superconducting Supercollider in the early 90s, we have some scientists who see the JWST gobbling up their funds, arguing we individually and together reject the premise that JWST must be restored at all costs. We further stand by the following positions, and away they go, right? I'll let you read through those. There were negative stories in the press, the telescope that ate astronomy. That is the idea that somehow the money that Webb was devouring, or I should say supposedly devouring, was stopping other projects proceeding. And one of the key reasons, as I'll discuss later, for the demise of the SSC is this kind of infighting. So there are definite efforts to prevent this growing out of control. You know, and again, the spectre of the SSC was haunting people. Support the Superconducting Supercollider. It had begun under the presidency of Ronald Reagan, carried on under the presidency of George Bush. It was going to be this enormous ring around Waxahachie in Texas, 50 miles around, leading the mayor of Waxahachie, Texas, to argue that it was essential for the future of mankind to discover the Higgs boson. But the problem is, how do you How do you sell the Higgs boson? It is hard. It is really hard. Astronomers have it relatively easy, I think, because they've got all these kinds of wonderful images that we're familiar with, where you can say, look, here's what we're doing. But the Higgs boson is a different business altogether. And maybe we can talk more about that later. So the Superconducting Supercollider did try, late in the day, they did try to establish a coalition of supporters that will keep the project going, but it ultimately fails. And precisely why, it's always hard to say if there's one factor or many factors, probably a combination of factors why the SSC failed. Lack of international partners, some physicists who were not high-energy physicists saying, look, you should not be funding this project over here because it's going to gobble our monies over there. There was major congressional concern, if you remember, in the early 1990s about congressional budget deficits. Texas had been very powerful politically when the project was initiated. The Speaker of the House, Jim Wright, was from Texas. The Vice President, George Bush, was from Texas. But by the time it was cancelled, those people had moved on. There were no international partners, really, for the Superconducting Supercollider. Also, and this is a judgment of somebody who's really studied the Superconducting Supercollider very closely, this is historian and physicist Michael Reardon. And so after a great many years looking at this, interviewing all sorts of people, going through all sorts of archives, his thought, the project was just too large and too expensive to have been pursued primarily by a single nation. However wealthy and powerful, the SSC, he says, is a bridge too far. Whereas in the planning for the James Webb Space Telescope, it was always taken that there would indeed be international cooperation. So even if we go back to 1989 in that conference I mentioned, one piece, there was a page of what was called sage advice, things we should definitely do. And one thing that shows there from the astronomer John Bacall, who we've already met, international cooperation may be critical for such a major project. And that's how it worked out, at least in the political economy of science in the 1990s and the 2000s. Now Hubble, because Hubble had involved a kind of series of life and death struggles to keep the project moving and get it going, Hubble had actually, I would argue, transformed the astronomical community. Previously, it had been just a small group of power brokers, you might say, who pretty much ran the astronomical community. After Hubble, because Hubble had required this community-wide effort, people making visits to Congress people, speaking to staffers, writing newspaper articles, all sorts of other kinds of what you might think initially are political activities. Hubble had transformed the astronomical community. So astronomers knew how to do this stuff, I think. And so to overturn the JWST cancellation, you have a lot of people putting a lot of effort in. Would it have been the case that even if nobody had done anything, Senator Mikulski would have kept it alive? Well, who knows? But that was not the belief amongst the people who were very active in trying to keep the JWST alive. And so it was a really very wide grassroots effort, I think, to keep JWST moving. So what it means to be an astronomer, I would suggest, has been transformed. You can sit in your observatory, but if you sit in your observatory and pay no attention to these kinds of wider developments, you may not have your observatory for much longer. is part of the message of Hubble and JWST, I think. Also, what you might call the distribution of contracts on JWST was much smarter than on the Superconducting Supercollider. We've got a much wider spread. You know, this is just contracts in the United States. You can do similar kinds of diagrams, and they were done for the European Space Agency, because the European Space Agency is a partner. Also, the Canadian Space Agency is a minor partner on the project, whereas the SSC really struggled with this business of how can we build political support in these various places. So I'm really leaping forward a great deal in terms of the construction of the spacecraft, but I just wanted to show the primary mirror in the 18 segments of primary mirror with the gold coating, because it's aesthetically so remarkably powerful, I think, this image, and similar ones to it. And here maybe we can even see a bit of construction work. So this is just, less than 2 minutes worth. And what is this? Well, it's demonstrating that Webb is nearing completion. Right. This is the sun shield. Which had to unfurl when the telescope was in space. So, I mean, what I find so remarkable is it's highly precise work and a highly precise instrument that is so big, I think. And again, just some of the key things for the mission. Okay. And I think you'll need to move me on one, please. Okay. So, again, this date is going to be very meaningful to a number of you. Because we've got the launch, so having spent all this time, let's get in space. Let's have the launch of the James Webb Space Telescope, and this was on an Ariane rocket. This is an Ariane 5 French rocket. And the launch was almost perfect, which means that JWST has the potential to conduct its mission in space for longer than would have been the case if the launch had not been so precise. So we're actually getting a countdown. And this is where I have remarkable admiration for the people involved with Webb, because you've spent 20, 25 years building this thing, and then you're going to blow it up, more or less. Surely your heart's in your mouth just a little bit, even if you think it's really going to work, isn't it? Just a little bit. As I say, it was a near perfect launch. And it's on its way to a Lagrangian point that is roughly 1.5 million kilometers from the Earth. And again, remember this early history, it's the anti-Hubble. Hubble is in low Earth orbit serviced by the shuttle. Well, there's no shuttle, so what's the point of having it in low Earth orbit, which is not so good for infrared telescopes because you're going from the light to the dark when you're orbiting the Earth. Much better to be out far beyond the Earth. Okay, and then somehow this feels almost like the Jurassic period by this stage. But anyway, we've got a political statement again. The images, how do you demonstrate the telescope's working? You show images, right? This again underlines the difference, say, with the superconducting supercollider and the Higgs boson. But we're looking at a deep field here with the president. And so not only is it talking about the mysteries of the cosmos, as I say, it's making a political statement. And and the fact that JWST has been remarkably successful opens up a space for the next large observatory in a way that if, say, that launch had not gone well, if something had gone radically wrong with the launch or with the telescope in space, that space would have closed down, I think. This is a new one. I'd never seen cheerleaders with images before. But there they are at the Goddard Space Flight Center to celebrate those images that had been shown the previous evening by the president. And the vice president was there as well. I mean, this was high-level politics. Again, I'm sure lots of people have seen many of these kinds of images before, but I just wanted to show a few. Light curve from exoplanets detected, or a kind of schematic light curve detected. The exoplanet moves in front of the star behind, and so there's a slight dip in brightness which can be measured. These kind of deep field images, again, the very distant universe. Would have been absolutely stupefying to George Darwin in 1905. And that's John Mother, who has been the project scientist, really, or was the project scientist for almost 3 decades, and won the Nobel Prize for his studies with the COBE satellite of the Big Bang. And that's at the press conference following the cheerleaders and following President Biden. So, a few points just to pull things together. With these kinds of scale of projects, we're into regions of what I will call mega projects. I mean, they're just so big. I mean, Webb, over $10 billion worth. I mean, how do you make these projects scientifically, technically, institutionally, and politically feasible? That is, how do you get people to actually vote for your project when it comes to the end of the day? You've got to assemble these kinds of projects, I think, not just in scientific terms, but also technical, political, institutional terms. You're having to piece together really very complex systems. You know, patronage really matters. I mean, who's paying the money and how the Congress and White House works, I mean, they're enormously important. But maybe the main message is what I think Webb is an example of. Webb is so big, it's megascience. I think that distinguishes it from big science. But megascience demands really that the advocacy of a project, you just don't do it once. You have to do it again and again and again. Until the day that JWST is turned off, there will be people acting as advocates for it. I mean, what has also been, I think, successful for Hubble Space Telescope and JWST has been this management of scale. Really, one of the key things in the history of certainly 20th century astronomy is the ability to move to new scales successfully, even if initially things don't go so well. You look at, say, the scientific papers produced by astronomers typically before the Hubble Space Telescope, an individual, a small group. Hubble, you start to see relatively small groups and then some larger ones. Look at the size of the science teams involved with JWST, and you're looking at many tens, maybe 100. The scale has got a lot bigger for the science teams doing the observations. We also see people playing a whole range of new roles, people who are having to be science managers, you might call them, not just astronomers who were doing astronomical research. On these kinds of projects, you have this remarkable, I think, division of labor. And if you haven't got that division of labor with competent people in these various positions, your project is going to be in trouble. And I wrote this about a month ago. Perfect science policy making is not to be attained in this life. And what do I mean by that is that any big project, or at least this is the conclusion I've come to, I used to think that there was some perfect world where things would be set up really well at the beginning and all would go smoothly and it would all be great. It's never going to be like that. What sorts out the successful projects, I think, from the unsuccessful ones when we're talking about this kind of scale is who can ride the waves better? Who can deal with the problems that were going to come out of left field that nobody could necessarily have predicted, but that will appear? Can you survive? And I think the SSC had a very hard time. Anyway, it might well have failed because of the congressional concern about budget deficits, but I think they just could not ride the waves. HST, JWST, it was an example, I think, of people successfully riding the waves and keeping things moving. And I wish those working on the successor to the JWST all the very best, because they are going to need it.
Q&A. We're
Sorry.
going to do a Q&A.
Yes.
Okay, so I left this slide in, but it's very apropos, I think, since JWST managers were told to expect a 20% cut in the budget over the next 4 years, is it? Or maybe next year. In any case, I think in the current environment, we're going to all have to learn to be efficient in our use of federal dollars. With that said, there is time for a question and answer period.
My question is about scale. In the 19th century, scientists like Darwin and Wallace did a lot of their research alone or with very few other collaborators in comparison to now when every paper seems to have 30 authors. Does scale have any disadvantages, and if so, what are they?
Yeah, just on the Darwin-Wallace question. Darwin, I think we usually see Darwin, he's this kind of individual, he's working away in Down House in Kent. But what I think is more productive when we're thinking about Darwin is to think he's part of an international network. He's getting lots of specimens, information fed into him. He's really a hub. We don't see these other people. And so we focus in on Darwin. I think Wallace is a somewhat separate case, but Wallace is doing his own collecting, whereas Darwin is, after he's gone on the Beagle, he's doing this kind of international networking. And in fact, famously in 1858, when the letter arrives from, it's a package, arrives from Wallace, Darwin thinks, oh, Wallace has brought me a new specimen. He opens up this package. It's not a new specimen. It is a manuscript which, by Jove, looks just like his own theory of evolution by natural selection. So there are big scale activities in the 19th century, although we often have to look a bit differently at them in terms of, if we were thinking about scale in astronomy, even in the 1940s, 50s, even into the 60s, you would have maybe a night operator with the astronomer who's at the observatory, in the observatory cage, in the telescope cage, making the observations. And so it's very much of a single skilled sort of operation. But we've had this enormous profusion of telescopes and this new kind of division of labor that's emerged. And I got so excited about Darwin and Wallace because that's what I'm talking about on Monday in my class. I've now forgotten the thrust of the question, which was
Disadvantages of scale.
right. I mean, one of the things that a number of people have mentioned to me is, well, how do you train a graduate student now? Because before, if you're building an instrument to go on a rocket, I mean, the downside is you've got maybe 5 minutes above the Earth's atmosphere before the rocket re-enters. But you could imagine a graduate student, or maybe a small group, they're building an instrument that will go on the rocket. They will do everything. They will design the instrument, get involved in building it. They will analyze the information. But if you have a large scale of activity where you've got, say, 100 people on a team, you're going to be a specialist in some narrow little area. And so there are potential issues there. I mean, and how do you credit people when you've got a team of 100? Somebody needs to demonstrate to their PhD committee, I've done this stuff. Well, I mean, how do you determine it? It's not so straightforward when you're into these elements of big projects, whereas it's a lot easier if you've got smaller scale kinds of projects. At least that's how it seems to me. I'd be interested in what other people think about that.
It sounds like a good subject for discussion in the social hour, but it is worth mentioning that when you have these papers with 150 authors, many of them are not, that's not their only publication. They're on there because there are a lot of different contributions that were required to produce this paper. But in the process of doing that, the authors on that paper are also authors on papers with far fewer number of authors. So in the case of an instrument, they probably would have published things on detectors and specialized integrated circuits and things like that went into developing a detector. And then when the James Webb goes up, they're part of the team that made it happen. So they get to be one of the 150 people that are listed on the web page, not on the actual paper publication. And if you're an old man like me, you go, who was responsible for this? Oh no, I have to go on the web. I have to log in. Anyway, it's a good question to ask is what does it mean to be a scientist and what constitutes a contribution that makes you an author on a paper and what is required to get a PhD. But it's not a new problem. In my day, you could get a PhD in molecular biology by figuring out how to clone the gene, publish your sequence, and you're done. These days, you can clone a whole genome in 1/100th of the time it took to do that back then. So it's a kind of moving target. Anyway, I'm sorry, I'm not the speaker.
Yeah, could I just mention?
Let's go on to another.
Okay.
This is my fault.
Right.
Red microphone. We're going to count to 3.
Okay, Bob Hershey, I'm a member, and I wonder how the successes of the JWST and the Hubble are going to affect the next generation of space telescope.
I would suggest that these kind of what if questions are always very hard, or what if issues. But I think the fact that Hubble and JWST have been successful opens up a space for a successor in a way that if they'd not been successful, that space for a successor would have been closed down. Or it would have been much harder, or it would have taken much longer. And my key example there is what happens to the superconducting supercollider and how that plays out after the superconducting supercollider is cancelled. And so again, this point, success begets success. If you want to be successful, you've got to be successful. You see what I mean?
Getting from 0 to 1 is hard. We have the blue microphone in the back of the room.
Hugh Brooks, member. With the advent of more commercial space travel, should we expect to see a resurgence of faster, better, cheaper again? That kind of coincides with the faster, better, cheaper commercial space travel. And alongside that, do we have a potential to break free from the political side of the things that you were talking about, kind of holding back more instrumentation above the atmosphere?
I would say you're never going to break free of the political side. It's just maybe going to be a different politics, would be my sense. But I think you start to see the emergence. It's hard to say precisely when, because there's not really a very good, what you might call, or at least I haven't found a very good academic literature to do with private space, just because a lot of the people who are writing about private space have axes to grind, projects to promote. But I think it's fair enough to say that you see the emergence round about, say, 2010 of this kind of drive, which had been, I think, in part fueled by a kind of libertarian urge earlier, which was along the lines of, oh, if we just get rid of NASA, we could do all these different things. How that works out and whether you end up with these kinds of philosophies like faster, better, cheaper applied in a new way, I think that is an interesting question that remains to be seen. But clearly we've moved, I think, into a different phase.
Red microphone.
Michael Albro, member. I'm an experimental particle physicist. I was interested that you spent so much time about the SSC and story. I'll come to my question, but I was deeply involved in that because I was on a committee of experiments for the SSC. I was also part of the Higgs discovery at CERN, and so I both fingered both camps. And I agree with you that it should have been a global project. It was an overreach. We finally got the Higgs boson at CERN with a machine that's third the energy, but higher intensity. And other things like it should have been put at Fermilab, where we already had a site and so on and so forth. But my question is, you spent a lot of time on the SSC, but they're really different animals. And did the SSC story have any direct effect on the JWST story? And one point, of course, is that CERN is very robust because they have no one particular country can sink it, although, by the way, we're very concerned about America pulling out of it right now. But is the management of James Webb robust enough that it cannot be sort of, if the US pulls out, it's going to be a bad situation for the JWST. But okay, there's two questions in there really. The effect on the James WST and the Supercollider, is there a symbiosis there with an effect?
Well, I've had a number of people who were very much involved with what was then NGST in the 1990s tell me directly that they had paid close attention to the superconducting supercollider story. And they were aware of it. And I've had also people who were involved in this fight to restore funding in 2011 tell me that, again, they were very conscious of the superconducting supercollider. And I was also wearing my historian hat. I was asked to provide any information that I had on the SSC to a number of people when they were fighting this fight about getting funding back in. JWST, it's principally American money, overwhelmingly, well, not overwhelmingly, but the great majority of the money. So it would not so much be the Americans pulling out, but if somebody said, oh, we've had enough of these Europeans, or we've had enough of these Canadians, that, we're just going to go it alone. And I think at this point, I find that hard to envisage, but, who knows what's possible and what's not possible.
I was at CERN last week, and people are very concerned, of course, because although the US is not a member of CERN, they're observers, and we pay about 30% of the big experiments as well.
Yes.
So if the worst happens, then it's going to have a huge effect on particle physics worldwide, actually. So we have to hope. Thank you.
Right.
I have a question in the interim, which is Mikulski played a huge role in saving the project. Do you think there was any was a lack of a similar person that doomed the SSC?
I think it's hard to say one thing. I mean, I would be interested in a view of one of the participants, but I think it's hard to say that this one thing alone doomed the SSC. I think it was a combination of things, and also this it was really hard sledding at that point, just because there was so much concern about congressional deficit or the budget deficit, and you had a Republican Congress. If you think back to the campaign 1992, what had happened, it had been Ross Perot running on almost a single issue campaign for a long time. Budget deficits. We've got the budget deficit has got to be brought down. So there was a great deal of concern about bringing the deficit down, and the Congress wanted to demonstrate it was serious about making cuts. And here was this large-scale scientific project, and it came down, I think, to a choice, either the International Space Station or the Superconducting Supercollider. And the International Space Station, you saw how adept NASA is at spreading out their contracts. The SSC had not done that to anything like the same extent. And so it was, you could say, an easier political
So maybe
target.
not, but maybe.
Yeah.
Okay.
Timothy Thomas, I am a member. I posit if the James Webb had failed, would it seem likely that the Chinese would have attempted a clone? But since it didn't fail, they didn't do anything in the space telescope area. But are they planning, to your knowledge, a successor to the James Webb?
I'm not aware of any Chinese efforts really in space astronomy. I don't know if people who are closer to this than me might. Let me mention Eric Smith is recently just former member, senior member of the management team on JWST. So Eric can enlighten us here, maybe.
Yeah, hi, Eric Smith. I'm a member, and as Robert said, just recently retired from NASA. Right now, the Chinese are primarily concentrating a lot of their astronomy efforts on ground-based work, and they have some very large telescopes there. So they are technological competitors in astronomy. Right now, I don't know of anything comparable to Webb, and even if they were to be interested in that, it takes about 20 years to go from start to finish. So we still have a head start there. And like you were saying, why would they build one thing that's already there?
Right. I mean, there is a very large radio telescope that the Chinese have built, for example. And so, as Eric was saying, it's an effort more on ground-based telescopes, I think.
We're going to take a question from the YouTube chat.
Our first question comes from Michael Haken, a member from Silver Spring. Apologies if this was covered in the talk, but how did the world's first space telescope, the International Ultraviolet Explorer, influence the James Webb Space Telescope?
I'm not sure it directly influenced JWST, but it was certainly there with the Hubble Space Telescope, because some of the people who were involved in the International Ultraviolet Explorer were people who went on to work on the Hubble Space Telescope. And I think I'm right in saying that Lyman Spitzer, who is in many ways the kind of scientific inspiration for the Hubble Space Telescope, was very much involved with the International Ultraviolet Explorer. Somebody who was a major figure in NASA headquarters for a long time, very much involved in the development of space astronomy, somebody called Ed Weiler, was very much involved with the International Ultraviolet Explorer. So I think that sometimes it's not so much the technology, but it's the fact that somebody has worked on a particular project and learned a new set of skills that they then apply to a different project that is the important factor. Because it's a different wavelength, really. I mean, the International Ultraviolet Explorer, you know, ultraviolet, JWST, infrared. But I think you get this transmission of skills, knowledge, and abilities, and people get the chance to develop how they go about these kinds of projects.
Thank you.
Is that the only question from the web, or is there another one?
No, I think that's the only one.
Okay, do we have any other questions? Hearing none, allow me to thank you very much for this talk.
Thank you.
And before you go, there are a few gifts that we have for you. One is a framed copy of the announcement of your talk, signed by all the members of the General Committee on behalf of all the members. Another is a copy of Volume 17 of the PSW Bulletin, which brings together in one place many of the seminal papers, a couple of histories of PSW, a list of Nobel Prize winning speakers, all our Henry speakers, and some paired minutes of presentations on topics way back at the beginning of PSW, and then later addressing the same topic. And we have a paper by our very own Mark Rothenberg, who is here in the audience, that opens up the volume and talks about scientific societies and PSW. And finally, we have a copy. We have an actual ribbon of PSW, which has on its side 3 stripes that are evocative of the symbol for induction, which was studied by our founder, Joseph Henry, on this side of the Atlantic. And the unit of induction is the Henry. So with that, thank you very much. And before you all go, there are just a few things to mention. The next speaker is Joanna Drucker. I suggest you all take a look at her rather extensive history and contributions in art and in art criticism and in the history of language, especially written language. It should be a very interesting talk, something of a departure for us, but nonetheless. She is a distinguished research professor at UCLA, and she'll be talking about alphabet histories, the origins of letters from antiquity to the present. The rest of the schedule has been completed except for our Joseph Henry, which should be up within the time that we have our next meeting. The 2512th meeting will be on March 21st, and the speaker will be David Bennett, who is at NASA Goddard, and he'll be speaking about using gravitational microlensing to detect exoplanets. And I'm not going to read these all to you so that we can prepare to the social hour. Let me just mention one, the 2517th meeting on June 13th. The speaker will be Alex Creedley, who is the director of tokamak operations at Commonwealth Fusion Systems, which is attempting to develop a commercial fusion-based electrical generating system. He'll be speaking about their tokamak reactor, incorporating very, very high magnetic field magnets that were developed at MIT. And that is the second of our lectures on fusion energy production, which perhaps is wishful thinking. But it may turn out that wishful thinking was the wrong characterization of that. Anyway, it's an interesting field right now with a lot of developments, and we'll see how it goes. My guess is that these guys will get to break even before ITER, and I would be willing to give you odds on that. Anyway, I want to thank everybody for coming and thank our crew for manning the cameras and running the microphones, and to Robin Taylor, our executive director, videographer, and person who knows everything that needs to be known to put these on and who is in charge. And she's back there. You can't see her. But please, let's give everybody a good hand. And with that, I will accept a motion to adjourn the meeting to the social hour. Second, all members in favor. All members opposed. Meeting is adjourned to the social hour.